All right, so we're going to look at continuous probability distributions. Last time when we visited this, well, it was last year, we just looked at discrete ones. But before we get stuck into the continuous things, let's recap what all these things are. So we are talking about random variables when we're doing stats. A quantity, and the value of that quantity depends on chance or probability. The probability distribution then is a listing of all the possible values that that variable could take and its corresponding probability. Let's use this as an example. Eggs in a supermarket are sold in boxes of 6. The number x, so x is going to be our random variable. It's the number of broken eggs in a box, and we've got a probability distribution. Here it is. The number of eggs, their boxes are 6, so it's possible that 0 are broken, 1 are broken, 2, 3, 4, 5, 6. They're all the possibilities. So this is a discrete distribution. The corresponding probabilities of that happening. 0 chance of being 5 or 6 broken. Now, probabilities. So the properties of the probability of our random variable equaling 0 or 1 or 2 and so on. Well, we know it's got to be a positive number. We also know the sum of those probabilities has to equal 1. And if the probabilities are the same, our example they're not, but if they were the same, then we have what's called a uniform distribution. Then we used it to calculate some things, and the first thing we talked about was expected value. And there's our formula. It was the sum of xpx, where px represents the probability of x. I guess that's what I'm saying. Now, it turns out that the expected value is the same as average in statistics, or mean. It's a measure of central tendency where the middle of the data lies. So back to our example, how many eggs would we expect to be broken if we bought 10 of the boxes? We've now added an extra row, the xpx row, and added those up. The sum of the xpx is 0.3. So we're saying we would expect 0.3 of them to be broken, but that's in one box. Our question is saying if we bought 10 of them, how many broken eggs would we expect? So we'd expect to have 3 broken eggs based on that data. Variance. So variance was the expected value of x squared minus the average squared, or another way of thinking about that is the expected value of x squared minus the expected value of x squared, because average is expected value of x. And this is the measure of the spread, so how spread out the data is. Now we tend to use standard deviation because we're squaring the x's in our variance, and so technically it's units squared. So this is why we have standard deviation, so we can bring it back to the same units, which is better for comparing data. So standard deviation is simply the square root of variance, or another way of saying that is the standard deviation squared is equal to the variance. Let's do our example. There's our eggs. We now have a third row, the x squared px column, which adds up to be 0.6. So the variance then is the expected value of x squared, 0.6, minus the expected value of x, 0.3, squared. And we get 0.51. But that's the variance. They want the standard deviation. So the square root of that to 3 decimal places, 0.714. Relative frequencies then. So theoretical probability is what should happen, we would expect. Relative frequency is the estimate based on data. So as the size sample increases, they should get closer and closer to the theoretical probability. More times you do it, closer you should get. Students in year 12, yes, just like you, were surveyed to find out the number of siblings students have, and here's the frequency distribution table. So it's now not a probability distribution table, but a frequency distribution table. So instead of having the probability of x, we have the relative frequency rather than the probability. And I've also done a cumulative relative frequency there as well. Construct a relative frequency histogram. So that was the one that's like a column graph. So there we are, I've drawn mine in there. And polygon, remember we plot the points at the center of the column. And so there it is. Calculate the total area of the histogram rectangle. So this is where it becomes interesting, Because if I was to find the area of all those rectangles, look what we get. Because effectively what we're saying is it's the sum of the probabilities. The width of each column is 1, which makes the data work nice. So I deliberately made sure that I had a width of 1. But the height, of course, is the probability of that happening. So we have effectively added the probabilities. Now, if the width of each one was, say, 2, then we get twice the sum of the probabilities, and so on and so on. But look at this. That relative frequency polygon, and this is why we join them up to the axis after and before. Perhaps you always wondered, why do we do that with a polygon? And this is why. If I now find the area under that, let's call it a curve, I'll do it using the trapezoidal rule. It equals 1. That's going to become important when we look at some of our, extension 1 probability, what have you. You see, there is a direct relationship between the area under the polygon and the area of the histogram. This is why we join it up, so we can get those areas to be the same. Construct a relative frequency histogram and an ogive for this data. So there's my cumulative one, so the columns obviously are getting bigger and bigger because it's cumulative, we're adding on. And the ogive, there it is, fancy word for a polygon. Notice with the ogive, we don't join it up to the center of the column. That one is like drawing in the diagonals. Calculate the 5-number summary and the interquartile range. Okay, there's that graph again, I'm going to use that. The minimum, remember the 5-number summary? That was when we were talking about quartiles. You have the minimum, Q1, Q2, which is the median, Q3, and the maximum. So I can read off the graph. Q1 would be 25%. If I go across, because we're talking about discrete data, I can say, well, that's 1. And the median would be 0.5, that's also 1. Q3 would be at 75%, so that's 2. And the maximum, of course, is 6. So there's our 5-number summary. From there, although it hasn't asked us to do it, we could then draw a box and whisker plot and those sorts of things. But the interquartile range, remember, is Q3 minus Q1. So 2 minus 1 is 1. And there's a little recap on our basic stats.